which we call it wave function. You know that in quantum mechanics we show that by this side. So it's a function of the coordinate actually and the time. So you need to find that. I'm talking about the quantum mechanics without the representation theory. So if you use a representation theory, it's a mathematical theory to explain the quantum mechanics and is more beautiful than what I'm writing here. So you will see another symbols, the Dirac symbol for like that, for the wave function and this thing. But don't be confused that they means the same things. Actually, this is, you call it state
or vector.
State vector, yes. And for any vector, you need to specify that where the vector is living. So such vector live in the place which we call it Hilbert space. There is a lot of things about Hilbert space, but we don't need it that. So I will use the Hilbert space as much as I need. And all this, it's the same, okay? Just state. You need to know the state and energy of the system. So as a person working in quantum mechanics, it's not important for me that other things like the position, actually there is no position, or there is no momentum for a system which is live in this tiny size. According to quantum mechanics, you never can measure the position and momentum at the same time with 100 precision. If you're trying to look at that, the electron is moving here. If you're trying to find its momentum, P, with 100% precision, you lost all the information about the position. So X will be remained undetermined. Undetermined. This is the Heisenberg principle, no? High delta P delta.
Because when we fix the position, velocity will be zero. And we cannot determine.
Little different that. If you measure the momentum with 100%, so there is no error in the momentum. Huh? Delta. Yes. You know the error from the lab. Yes. Any basic. So definitely from this, you get delta X infinity. Some people state that the quantum mechanics is some fiction, or quantum mechanics is based on this principle. Yes, this is a based on the Heisenberg principle. But I want to tell you something more to that. Heisenberg principle can be derived independently from this Hilbert space and these things. Comes from here and can be verified for any systems, And this is very, very similar to what we are talking about in the electromagnetism called noise or something. So this is what is they call it at the band width. You know, for example, to receive the radio signal, you needed to change the tune. So 91, for example, to 91.1 or something. This is, and if you change it at more or something, so the noise will come. You never can get this radio station. So this is actually delta of the frequency, what you are doing by the hand. So in a tiny level, in quantum mechanical size, I mean in the atomic size, you have it something like that exactly, which they call it uncertainty, but this is, you can call it error. But this error you never can remove even if you make your best instrument. So in this level, this is remained as some characteristic, if you can call it error, but I call it this uncertainty. So, uncertainty. So the main question in quantum mechanics is to find the state and the energy level. And energy, it's important energy because you wanted to know that for example, you want to know that with this energy, what you can do. And still it's very complicated. Look at that. From the very basic quantum mechanics, we know that the psi, I write this equation, so this is a Schrödinger equation actually, for the wave function. And the psi is a function of x, y, z, and t, x, y, and z. So this is the equation. So this equation is the second order partial differential equation. Again, I want to tell you that why the statistical quantum mechanics exists. Differential equation, second order partial differential equations. And only for very special case you can solve this equation. And this is for one particle. Look at that, there is a 1m here. If you have more than 2, yes, if you have more than 1 electron, for example, and you have 1 nucleon here,
Use effective mass.
proton. This is a model for hydrogen and helium, yeah? You have a 3 mass, 3 particle. For each particle you need to write the Schrödinger equation, but not like that, because they have interaction to each other.
Yeah.
These 2 electrons have repulsive attraction, they have attraction, interaction. So look at that for this 3 system. Even forget about the 3, just for 1 electron even. For two you can solve that. But if you have more than that, actually you need to solve like that. Psi total, this is the total state. And here you will have 1 mass and second mass. So how I can write that? I can write sigma and I, 1 to, I don't know, any number, if you have more than 1, minus h bar. For each one you have a mass. Huh?
Yeah.
And you have this operator. This is actually the second derivative with respect to the x, y, and Laplace operator, Laplace-Beltrami operators. Plus potential, huh? And potential is very complicated, no? I will tell you why. Multiply to psi total. So psi total here will be, look, will be psi for particle 1 at position 1 and the time, psi multiply to, not always this also. So it will be something like product of the psi for different systems. Even if it is possible, you know. Writing this equation have very if. It shows that the first mass or electron should move independently from that or not very connected to that. Otherwise, you never can write that solution for this equation. But okay, for very softly we can write that solution for that. And look at that. Vi is the potential, so potential will be sigma all the possibilities. So if we call it this particle 1 and 2 and 3, so you know how many possibilities you have. 1 interaction, 1v, 1v, and 1v. So will be sigma, for example, via j to I, j from 1 to n. But j should not be I, But this is also a problem. It means that you never can consider the interaction of this with itself.
Yes.
If you have a single electron, the single electron make electric field around the space. You never can talk, I mean we can, but it will be infinity actually, to talk about the interaction of the one particle with itself. So here we exclude the self-interactions. I to I, we never consider that, the interaction of the V to itself. So look, just for one particle, you can exactly solve this equation. If you go to the more than one, it's very difficult and almost impossible to find the solution for the Schrodinger equation. If you cannot find that, it means that the quantum mechanics main question remain unsolved. Main question was to find psi. So if you have more than one, I want to tell you that for two you can do. For two you can do, and you know exactly that hydrogen atom can be solved exactly. If you have electron and proton here, you can, and the potential, what is the potential? This is the potential, R minus 4 over pi. This is a Coulomb, just look at that. This is a Coulomb. This is a two particle system, And if you fix it, I want just to, before you learn things, I think you need to learn the difficulty which you will have. You see, I was very tricky. First I made this two for you. I said this is the potential and you can solve. But not all that. Where is the coordinate system? I need to put the coordinate system here, no? Now it makes difficult. For this electron I need to write one vector, no?
Yeah.
R1. One step more it will be complicated. And this R which I write here is actually R2 minus R1, no? The difference of these two, if you write it. So I started from this picture because I want to keep you to follow my talk, but after that I needed to add. But I want to tell you that with that, if you be a little bit clever, you can solve the Schrodinger equation for n equal to 2. We have a 2 particle. So this equation can be solved. 1. Where is the potential? Potential is minus 4 over pi. Yes, R2 minus R1. Psi total will be IH1, run the psi total partially from T. So this equation you can solve, but not in this form. In this form it's not clear to how to find the solution. Fortunately, we can use another system coordinate. Instead of putting the coordinate system here, that will be your first task to do. I explain now, and I will ask you to go home and do the calculation, because you can find in any textbook of quantum mechanics, classical mechanics, you can find it. Just go one more step more. So for one electron and one proton, this is the Schrodinger equation. And just be a little bit clever and don't use R1 and R2, and instead of that, use a coordinate transformation. Look at that. The first picture, the easy picture like that, after sometimes turns to that. And now I want to make it more complicated. You never can put it that. You needed to sit another place and look at that. So this is the evolution of the problem. So if you be little clever and pass just to R2 minus R1, and another R, M electron R1, M proton R2, M electron plus M proton. And if you remember that the proton is almost heavier than the electron, MP over ME is 1,840. Okay, this is 36 or 32, I got 40. So proton is very, very heavier than the electron. So here I can forget about the electron and just write that the proton here. Yes?
Yes.
And I can define a mass. This is my mass. I call it reduced mass.
Or effective mass.
Effective mass. Yes, reduced mass. You need to be very careful where you are talking, In quantum mechanics and quantum electrodynamics and quantum field theory and many things, we have two types of the mass, which is called a bare mass and a physical mass or effective mass. So I didn't use I confirm your statement. I didn't write that as effective. But effective is something else, actually. Reduced mass. So I want to ask you, go through this equation and try to use this coordinate transformation. You can find in any system. Finally, you know what you will find? I write for you. You can transform this equation to the other form. So that will be your small task to do. You can go and reduce the Schrodinger equation to this system. You don't need to remember all the equation like me. I love, because when I was a student, every day I remember one equation. So that's the reason that I remember all, not this. Personally, if I look the equation one time is enough. Next time I don't need to read. But you don't need to be like me. If you like, you can be. It's a hard life to be like me. I don't recommend you to be like me. So look at that. What we will find is we'll build something like that. Okay. You see, one great achievement or advantage is that I started from the system with two particles and the one equation, yeah? Mm-hmm. One equation for that. I splitted the system now to two equations. That's good. And the interesting thing is that in the first equation is related to this coordinate, huh? Yeah. Relative. And the second equation related to this. You know what is the name of this in physics? Center of the mass. Yeah. Huh? Yeah. Center of mass. So I split the dynamics of the hydrogen atom to the dynamics of really two independent systems. The first independent will be the motion or the state of the relative position and the state of the center of the mass.
So, doctor, we need to find the Schrodinger equation for two particles, independent particles.
We have one single equation for the system with two particles. Particle means electron and proton. Mm-hmm. Yes. We use the coordinate transformation and reduce the problem to the two equations. Mm-hmm. And in these two equations, now instead of the particle 1, you have center of mass. And instead of the particle 2, you have the relative position or relative. This position have this mass. This is interesting. And this position have this mass. MAE plus MAP. So I want to make a more beautiful picture now. Is that a system with two particles reduced to the dynamic of two systems with two particles reduced to the dynamic of the reduced mass with this coordinate and total mass with this coordinate. And you know, in dynamic of the total mass, I mean central, you never see any trace of the reduced mass, yes? There is no reduced mass. There is no argument here. There is just capital R. So you definitely, immediately can solve this equation. You can immediately solve it. That can be solved very easily. And this equation can be solved very easily. So this equation, we don't consider this equation. You know, the solution of this equation means the solution for the center of the mass. We talked about the proton and electron. Proton is still very heavy. Yes?
Yes.
So when it's very heavy, so it means that the center of the mass would not change. center of the mass will be located over the proton. Huh? So, and the proton is fixed, proton doesn't move. So you can say that this solution gives you the wave function for center of the mass, and it doesn't move. So actually, the phi doesn't change. If there is a initial phi, after some time will remain the same, because the center of mass doesn't move. But this equation no. A little bit change in the state of the reduced mass definitely will change the whole scenario of this. So just I want to present the solution, and but you needed to find that. So you can solve that equation. You can solve this equation. So two-body system are solved. So one body system you can solve, but not solve. At least almost solvable. Because even with one particle, we have the case which we cannot solve. I can give you. For example, exceptional case of one dimension are the case which the potential is time dependent or potential, but almost solvable. I mean, this is a two-body. The main important example of two-body is hydrogen atom. Yes.
Yes.
So it can be exactly solved. Everything. I mean, you can find the state side, and you can find the energy. So your task is just to go and find the solution for this differential equation. I mean, the wave function of electron. You can find in any book, elementary. But look at that. For the particle greater than the 2, the Schrödinger equation cannot be solved. So you need the approximation methods. There are, finally, from whole my talk, I can tell you that classical and quantum mechanics give us exact or almost exact results only when the number of the objects or systems are few. Few means
One or two.
one or two. And for example, you know, there is a problem called three-body, like moon, earth, and sun. It cannot be solved exactly. You cannot find exact the path of that. It's an approximation. So we talk about the particle, but look at that. If we have one hydrogen atom here, and we have one hydrogen atom here, and we have one hydrogen atom here, so we have a 3 hydrogen atom. They give you 3 ball as a 3 hydrogen atom. And they give you this information that the first hydrogen atom energy is in the first level. I mean, energy for that is minus 13.6 electron volt. The energy for the second one, I mean, the second electron is prepared in this energy, 3.